Hello everyone and welcome to our presentation on matrices and their wide-ranging applications. I am Nafis Muqtadir and along with my friend Salman Tahamid, we are excited to show you how something as simple looking as a grid of numbers can have such a powerful impact on the world. When we first learned about matrices in math class, it often feels abstract, rows and columns of number with confusing rules. But today we want to change that perception. You will see how matrices are not only central in modern mathematics but also crucial tools in fields like computer graphics, artificial intelligence, engineering, physics, and even bioinformatics. They are used to build simulations, encrypt messages, train AI, and model the economy. So let's begin our journey into this fascinating world where numbers meet real life. Computer graphics and animation. Let's start with one of the most visually exciting applications, computer graphics and animations. Imagine you are playing a 3D video game or watching an animated film like Toy Story. Behind the scenes, every rotation, movement, or camera zoom is powered by matrix transformations. In 2D and 3D graphics, matrices are used to apply geometric transformations. This means we can rotate characters, scale objects to make them bigger or smaller, and move elements across the screen. Want to spin a spaceship or simulate camera movement in a scene? That's matrix multiplication doing its job. Even lighting shading, and perspective. Those cinematic effects are calculated using matrices. So the next time you are immersed in a visual world, remember, it's all made possible by rows and columns of numbers working perfectly in sync. Cryptography and cyber security. Moving on to something more covert, cryptography. In cybersecurity, matrices are used to ensure to encrypt and decrypt information. This makes sure that sensitive data remains secure and reliable to unauthorized users. One classic example is the Hill cipher, where the original message is converted into a numeric matrix and then encrypted using matrix multiplication with a secret key matrix. Only someone with the correct inverse key can decode the message. The principle extends into more advanced encryption algorithms that protect online transactions, secure communications, and digital identities. In an age where cyber attacks and data breaches are on the rise. Matrix-based encryption remains a silent but vital shield protecting us. Engineering and structural analysis. In the field of engineering, matrices serve as the foundation for solving systems of equations, whether it's electrical circuits, mechanical systems, or civil structures like bridges and buildings. Engineers rely heavily on matrices to simulate, analyze, and design solutions. One key method used is the finite element method or FEM. In this approach, a complex structure is broken into smaller, manageable elements. Each element is described using matrices that represent how it responds to force or stress. When combined, they give a global picture of how the entire structure behaves. Image processing. Now let's look at something we all interact with every day: images. Every digital image is just a matrix of pixel values, whether it's black or white or colored. Each pixel brightness or color is represented numerically and arranged in rows and columns. Image processing techniques use matrices to modify these pictures. Want to blur an image, sharpen it, detect edges? These effects are created by applying what's called a convolution operation, where a small matrix known as kernel is slit across the image matrix to produce a filtered output. From Instagram filters to facial recognition and even medical imaging, these operations are possible thanks to matrix math. Artificial intelligence and machine learning. Artificial intelligence and machine learning wouldn't function without matrices. In fact, every neural network you hear about is made of layers of matrices that store data, weights, and biases. When an AI learns to recognize a cat, translate a language, or recommend a song, it's essentially performing thousands, sometimes millions of matrices multiplications in the background. During training, the AI adjusts its weights through a process called backpropagation, which uses matrices to fine-tune itself based on errors. Libraries like TensorFlow, PyTorch are built to optimize matrices operations because the scale and speed of computation matters greatly. So the smarter AI gets, the more depends on efficient matrix mathematics. Economics and input-output models. In economics, matrices provide a way to understand how sectors of economy interact with one another. A famous model is the Longchef input-output model, which uses matrices to represent how output from one industry serves as an input for another. Imagine you are analyzing a country's economy. How much steel does the car industry need? How does agriculture fit into manufacturing? All this can be modeled and predicted using matrices. This helps economists forecast growth, evaluate policy impact, and optimize resources allocation. So, behind every macroeconomic forecast or GDP simulation lies a web of matrices helping model complex interdependencies. Graph theory and networks. Social networks, transformation grids, and internet infrastructure all have something in common. They are made of interconnected nodes, and matrices are the best way to represent those relationships. In graph theory, adjacency matrices are used to show which nodes are connected. For example, in a social network, each person is a node, and if two people are friends, there is a one in the matrix. If not, it's a zero. This simple structure lets us run powerful algorithms to find shortest paths, detect communities, and even predict how information or diseases spread. Metric operations let us analyze entire networks efficiently, making them invaluable tools for everything from logistics to epidemiology. Quant- Graph theory and network. Social networks, transformation grids, and internet structures all have something in common. They are made of interconnected nodes, and matrices are the best way to represent those relationships. In graph theory, adjacency matrices are used to show which nodes are connected. For example, in a social network, each person is a node, and if two people are friends, there is a 1 in the matrix. If not, it's a 0. This simple structure lets us run powerful algorithms to find shortest paths, detect communities, and even predict how information or diseases spread. Quantum mechanics and physics. In the quantum world, matrices are more than just tools. They are the language of universe. In quantum mechanics, the state of a system is described using vectors and its evolution is governed by operators which are represented as matrices. For example, Hermitian matrices are used to represent observable quantities like energy or momentum, and their eigenvalues are given measurable results. Unitary matrices describe transformations that preserve probability, making them essential in quantum computing and information. Quantum computers, unlike traditional ones, perform operations on qubits using matrix transformation, and that's what allows them to solve complex problems exponentially faster than classical systems. Robotics and control system. In robotics and control system, matrices are used to model motion and control responses. A robot arm, for example, has multiple joints, and the position of its end effector depends on angles and lengths. This relationship is represented using transformation matrices. Control systems also rely on matrices to represent dynamic equations. When you want a drone to hover in place or self-driving car to make a turn without tipping over, matrices define the control parameter that keeps everything stable. So whether it's an individual robot assembling car or a robotic vacuum mapping your living room, matrix math is silently guiding every move. Weather forecasting and climate modeling. Predict the weather. Predicting the weather is one of the most computationally intense tasks we do. Meteorologists divide the Earth's atmosphere into a grid, and each grid cell holds data like temperature, pressure, and wind speed, all stored as massive matrices. These matrices are then plugged into differential equations that model fluid dynamics and thermodynamics. Supercomputers process these equations over time steps to simulate how weather systems evolve. Even long-term climate models that predict global warming rely on these matrix-based simulation approaches. So next time you check the forecasting or see a climate projection, know that it's come from solving matrices equation on a global scale. Traffic flow and urban planning. Urban planners use matrices to model and improve how people move through cities. Origin destination matrices record where trips start and where they end, helping design road networks, public transit, and pedestrian pathways. These matrices help simulate peak traffic loads, optimize timing, and plan future expansions. They are even used in riding sharing algorithms to match to match signal and plan future. They even used in ride sharing algorithms to match drivers and passengers efficiently. Thanks to matrices, cities can become smarter, more efficient, and better equipped to handle population growth. Genetics and bioinformatics. In the life sciences, matrices are used to analyze genetic information. DNA sequences can be represented as matrices where each row is a gene or a nucleotide position. Sequence alignment algorithms use matrix scoring to compare genetic material and identifying mutations or common ancestry. Gene expansion data, which measures how active different genes are in various conditions, is stored in large matrices that help researchers identify patterns and potential treatments. So, whether it's finding a genetic disorder or mapping out family tree, matrices help scientists make sense of the building block of life. Recommendation systems. Ever wondered how Netflix know what show to recommend or how Amazon guesses what you will want to buy next? That's matrix math again. Recommendation engineers engines use user item matrices to model interaction. If you have rated certain movies, the system uses matrix factorization techniques and decomposition to predict how you might rate other titles. It finds hidden patterns in massive datasets, something only matrix method can handle efficiently. Without matrices, modern recommendation system wouldn't exist, or at least wouldn't be as accurate and fast as they are today. Audio signal processing. In audio signal processing, sounds are converted into numerical representations, usually as waveforms. Matrices come into play, where we analyze these signals using tools like Fourier transform, which breaks a sound into its frequency components. This allows us to clean up audio, remove noise, and even enhance voice clarity. Voice assistants, auto-tune software, and even hearing aids rely on these techniques. So whether you are mixing a song or talking to Siri, matrix-based signal processing is at work in your ears. Conclusion. A universal language. As we wrap, it's clear that matrices are more than a math topic. They are a universal language for solving real world problems, from ancient pyramid alignment to advanced AI, from securing digital data to forecasting weather. Matrices provide a powerful, flexible framework for modeling and transforming information. Now, please don't stop talking about Palestine. They have the right in this world as we do. We hope this presentation has opened your eyes to the depth and versatility of matrices. Thank you for listening. Thanks again.